Welcome to Spectrophotometric Analysis of Commercial Aspirin. This is Barbara at PASCO. I wanted to begin with sharing the agenda. First of all, we're going to show you the UV-Vis Spectrometer, PASCO's spectrometer that goes down to the UV and visible range, and also in the infrared range to study particles in solution or analyze light sources. We're also going to look at the spectrometry software, the app that's free that you use to connect to that spectrometer and do some analysis. So after I introduce you to the tools and software, then we're going to go into the solution preparation. How did we make the solutions that that you see being analyzed in this investigation? And then you'll see me using tools for data collection and analysis in the spectrometry software. So I'll walk through just those tools that you need to get this investigation done, but there's a lot more to that software, and you can check our website, and I'll point you to some resources at the end on where to get more information on the other things that spectrometry can do. And speaking of more things, more resources on pasco.com, I will show you how to access the experiment library on our website, and where you can find more spectrometer labs, more than just this analysis of aspirin tablets, but not only for the spectrometer, but for all of our equipment. You can just find activities that you may find helpful. And also, then I'm going to switch over to Roger, and Roger will discuss a little bit more about what can you do with the UV-Vis spectrometer, going a little more into the theory behind the chemistry and physics of the phenomena that's occurring in the instrument while you're performing these experiments, and more help and resources. Okay, so I'm going to switch cameras now so you can see the UV-Vis spectrometer. Give me 1 second. Okay, and you'll see there's also a lot of equipment there set out on the display. So here's the UV-Vis spectrometer, and on the screen here, it's this spectrometer includes 10 semi-micro cuvettes, shown right here, and the USB cable that you need to connect to your device, the power supply to plug it into AC power, optional accessories that you may want, which I'm using in this investigation, sold in packs of 2, the quartz cuvettes. I'm using the quartz cuvettes for this investigation because we're going far down into the UV region. Both of these cuvettes will work for this investigation, but I specifically wrote this around the quartz cuvettes, and they do perform slightly differently. So keep in mind I'm using quartz today. Now, another accessory you can get is the fiber optic cable if you want to study light. Today we're studying solutions, but you can also study light sources and see where the intensity is maximized, or even look at specific wavelengths that are peaks for a particular light source. If you want to know more about the specifications, here's a few of them, but I would recommend going to our website, pasco.com, and looking for the product SE3607. That is our UV-Vis spectrometer. Here you can see that the UV-Vis spectrometer is compatible with our data logger, which has a USB-A port on the device itself. So that's what you need for your device to be compatible with UV-Vis spectrometer. You need that plug for the USB. So that means not only our data logger, but also Windows computers and Mac computers. But your phone, in this case, your iPhones, those won't work with this spectrometer. We do have a model that will, and that's the wireless spectrometer. But today we're going to use the spectrometer that goes into the UV region. As I mentioned before, PASCO spectrometry software is free. The software itself does work on many more devices. You'll see that Android phones and Android tablets are included in the devices that are compatible with the software, but specifically the UV-Vis spectrometer does only have compatibility with your PC, Mac, or the Spark PASCO's data logger, Spark LXI and LXI2. You'll need version 2.3 or higher of the spectrometry software to work with this spectrometer. You'll have to check, make sure you can I'll show you how to check and see if you have the right version of spectrometry in a moment. You don't need a license, it's free, and you can download that software straight from PASCO.com. And I'll be using the spectrometry software today. Okay, I'm going to switch displays here. So give me one moment. And in the background, you can see spectrometry. And I'm going to show you how to check to make sure that you have the right, you have the correct version of spectrometry before we move on. So I've downloaded spectrometry software. I've already connected the spectrometer by USB to my computer. I just plugged it in, and this shows that I'm connected. If I go over to the right side where I have a gear and I click that gear, I can click About Spectrometry. And it tells me I have version 2.4.0, which is higher than 2.3. And this is the most up-to-date version we've got so far. So I'm good to go. Okay, now let me go back to the presentation. Okay, so what is aspirin? Aspirin, the chemical name is acetylsalicylic acid, or ASA for short. So I'm going to be saying ASA, I mean aspirin, or acetylsalicylic aspirin. So it's produced through an esterification reaction between salicylic acid and acetic anhydride in the presence of a strong acid, and also warmer temperatures like 80 degrees Celsius would be appropriate here. So it's an esterification because we've got an ester coming and rearranging places with the hydroxyl and salicylic acid. And that's how the acetylsalicylic acid molecule is produced. Here's that ester group, and here is that hydroxyl group. Now our products are ASA, or aspirin, and acetic aspirin. You might be interested in doing an experiment where you make aspirin, and you can do that experiment, but today we're just talking about pre-existing aspirin that you buy over the counter at the grocery store. And that's the great thing about this experiment, is all the materials to make the solution, they are from the grocery store. They are common, easy to get materials, nothing too difficult here. So the principle behind what we're doing today, how we're going to do the analysis. Well, because absorbance is directly proportional to concentration according to Beer's law, we can make a calibration curve of 5 known solutions of known concentration, and we can plot those absorbances for each of those concentrations and get a graph of concentration on the x-axis, absorbance on the y-axis, and we can plot those 5 known solution absorbance and concentration values, and we can make a linear fit, and we can use the line equation to determine the concentration of an unknown solution of aspirin. That's the goal. We're going to try to figure out how much aspirin is in an aspirin tablet from a bottle that you would get from the store using known concentrations of acetylsalicylic acid. So you can get your acetylsalicylic acid from your favorite chemical supply company. And all solutions are made with ASA, acetylsalicylic acid, and isopropyl alcohol. This is 91% isopropyl alcohol. It's the same kind you get from over the counter at a grocery store or a drugstore. So that's the solvent we're using, isopropyl alcohol, and 91% for the best dissolving in solution. Okay, so I will show you the directions for this investigation as we get towards the end of the presentation. There is a lab written with directions and all the materials listed and all the procedures and everything. So in the teacher version, teachers are directed to make the stock solution of salicylic acid. And the directions say you get barely any of the acetylsalicylic acid, just 0.400 grams. So you need a balance, an analytical balance that reads to the 10,000th place in order to do that. And then you dissolve it in 91% isopropyl alcohol using a volumetric flask to make the stock solution. Now the concentration of that stock solution will be 2.2 times 10 to the negative 3 molar. It's very low concentration, but that's okay because this is the minimum concentration we need to get a nice 5 solution plot with this spectrometer. If you're It's easier to work in millimolar because having to write that exponent, I don't know about you, but to me, having to write that exponent, if I could save a second or two on writing down my observations, I will. So I'm going to work with millimolars. 2.22 millimolars is the stock solution concentration. So after you've got the stock solution, then the instructors are directed to make a series of 5 dilutions, solutions A, B, C, D, and E. And each of those solutions has an increasing amount of stock solution. So solution A, you can use the transfer pipette to collect 2 milliliters of stock solution diluted to 100 milliliters with isopropyl alcohol. Solution B is 4 milliliters of stock solution diluted to 100 milliliters, and all of these dilutions are going to be done with the 91% isopropyl alcohol. I'm going to do 6 milliliters diluted to 100 in solution C. We're going to do 8 milliliters in solution D, and in solution E, it's 10 milliliters diluted to 100 with the isopropyl alcohol solvent. So that is how you prepare all of the 5 solutions that we say these are the known concentrations in order to do the Beer's law plot for our calibration curve. Okay, when you follow those directions on preparation, you will see that the absorbances of the known values should fall in this range between 0.2 and 1. And because we're measuring absorbance, we don't want to exceed 1. If you have a solution that's greater than 1.0 on your absorbance, you definitely want to go and dilute your solution until you get below 1. It's just not enough light is getting through past absorbance of 1 to be accurate, and it's no longer linear past an absorbance of 1. And the same thing on the lower end of the range. As you get lower and lower below 0.2, there's just so few particles there. You just make a lot of room for error there, and you want to minimize your error by staying within this range of absorbances. Acetylsalicylic acid, you will see in a spectrometer in a moment, the maximum absorbance of that molecule is around 229 nanometers for the wavelength, but we're going to measure the actual peak wavelength. We should see it's going to be around 229 nanometers. That will vary not only based on the solvent you use, but even the container you use, or how long you let your spectrometer warm up. My spectrometer has been on for a while. You want at least 10 minutes warm up time, the more the better. So so I explained already how to make the solutions A through E. So I'm going to set those aside and get them out of the way for now. And now I've got solutions A through E here. I've got little samples in the quartz cuvettes. And the quartz cuvettes have clear sides and frosted sides. So you'll notice that when I handle the cuvettes, I'm handling by the frosted sides. And of course, remembering to use a lint-free, scratch-free wipe as you fill each cuvette. I've already cleaned mine to make sure that there's no extra fingerprints or anything else that might accidentally block light when the light goes through these cuvettes. Okay, so I'm going to do the procedure here. And again, like I said, there is a write-up, and I'll show you where to find that lab write-up as we move along here. So the first step is to calibrate the spectrometer with the solvent. Remember, the solvent was 91% isopropyl alcohol. Let me do that. Okay, so my spectrometer is connected. When I've opened the spectrometer, it starts with Analyze Solution. It opens up to this tab automatically. And the first thing I need to do is calibrate. Let's say that I forget to calibrate and I just say, oh, I want to get started. I'm going to hit the record button and start recording. It's going to remind me I'd better calibrate because I need to make sure that when I measure each of these solutions, I'm not getting any interference, or I'm eliminating any interference that might come from the cuvette or from the exterior outside of the spectrometer, from the light out there, or the solvent itself. The solvent may be adding interference, or it will affect the light going through. So here's the spectrometer. This is this side with the light icon. This is where the light source is. The light goes through the solution, which is a 1 centimeter length. So the path length for Beer's law is 1 centimeter. The detector's on this side where you see the rainbow. So light goes through the solution. The more particles there are in the solution, the less light gets through to the detector. And the instrument is measuring transmittance, but we're going to be reporting in absorbance today. So let's get calibrated. I just put my solvent, 91% isopropyl alcohol, in the spectrometer, and I'm going to first calibrate dark, and then calibrate my reference, in other words, my blank or my solvent. And now I'm eliminating any information that may be coming just from either the quartz cuvette, from excess light, or from the solvent itself. Those icons for calibrate dark and calibrate light are also found here on the bottom down below. You can also calibrate with these. So every time you do a new solvent, you need to calibrate, but this whole experiment is done with the same solvent, so no need to continue to calibrate between runs. Now the next step, let me bring back the directions. So I've done step 1 here. Step 2, the next bullet, set the analysis wavelength with the second most concentrated solution. In this case, letter D is the second most concentrated solution. And the reason why is because we want, like I explained before, we want to avoid the extremes, right? Because we want to be sure we're well within that range of 0.2 to 1. And you'll notice here's my trace of the absorbance of the solution that I've just put into the spectrometer. Now, I mentioned that the spectrometer measures transmittance. So if I wanted to look at transmittance, I would go to the y-axis here where it says absorbance and just click that to change the transmittance. But I really, in this investigation, I want absorbance, so I could toggle back just by selecting it. Okay, and I can expand the view by hitting the scale. So that's this icon with the X that's expanding. And now you can see I've got a really high peak. My major peak is right here. Oh gosh, it looks, here's my wavelength along the x-axis. You'll notice that my range is well a little below 200 and well into the infrared, around 1050. I want to analyze at the peak of that acetylsalicylic acid molecule. So looks like my absorbance is good. It's kind of dancing around there at the top though. And that's because, remember, there's barely any solute in these solutions. So I'm going to experiment with the number of scans to average here on the left side. That means this peak will be more averaged out over more than one reading. So I am averaging 6, 7. You'll notice it gets more stable as I increase the number of scans to average. If I increase the smoothing, that's also going to broaden the peak a bit. So if I've got a peak that's dancing left to right a little bit, even though it's average, if I increase the smoothing, that'll flatten it out a bit. I don't want to do too much, so I think this looks good. I've got a nice stable peak that is varying a little bit, but not too much. So I'm happy with the smoothing and scans to average. I'm going to hit stop, and it stopped recording. So what I've done here, first thing I did was I need to choose an analysis wavelength. That means pick the wavelength that is the signature of the acetylsalicylic acid molecule. Now, you'll notice that this coordinate was by default on the screen. If I grab the gray box and I can move it, I click and I drag it, I can move it to the data. And if I let go, it will snap to the data. Now I want to move the box down, and I can nudge using the arrows on the left and the right above that box. I can nudge to get the maximum absorbance. Right now it's 0.741. That's a little bit higher, 0.745. Okay, it looks like the highest, the peak, the true peak is 0.745 as absorbance. And that wavelength is 233.8, and that's awfully close to 229 like we expect. So that's great. We can verify that this is indeed acetylsalicylic acid in here, and I click the check mark. And the check mark, now I've got this black vertical line, and it points out that I clicked at 233.8 nanometers wavelength. That is the wavelength I'm going to be analyzing all of these solutions at, because that is the indicator for the how much acetylsalicylic acid is in my solution. Now I've got my analysis wavelength. I can go to the tab up here and go to the concentration. Now I'm going to do a Beer's law plot, but first I need to customize a little bit. So there's this table that has concentrations. I said that I like to use millimoles per liter because molarity, it's hard to put in those exponents. I'd rather just not use exponents, and in that case I can do millimoles per liter. And you can calculate if you use the dilution equation, M1V1 equals M2V2, you can get the concentrations of each of the solutions I made. So solution A, or the first one, is 0.044 millimolar. And solution B is 0.0 0.089. How did I get these? Well, I just did some chemistry math. I did my M1V1 equals M2V2, starting with the concentration of 2.22 millimolar in my stock. Solution C is 0.13 millimolar. Solution D is 0.18 millimolar. And solution E is 0.222 millimolar. Now, if you wanted to, you could make as many concentrations to fit your plot that will fit in this table, but 4 or 5 is good enough for a Beer's Law plot. So now we're ready to measure the absorbances of solutions A through E. Okay, so solution A here, orient it correctly so that the light goes through the clear side of the cuvette and I can hit start. I'm going to wait for that number to stabilize. Okay, 2.76. Next solution B. And you'll notice as soon as I click the check mark, I go from a moving orange dot to a solid blue dot. That means I've recorded that value and it's plotting it on the graph. And I'm going to expand it once I have all of the data. Solution C. That one's moving around a little bit, but I'll click the checkbox. And D. Great. And solution E finally. And I'm going to keep that value. Okay, so you'll notice here that I've got some information. I have this rainbow box here. This is the preview of the wavelengths that I'm measuring at. It's showing me that my peaks are still at 234 nanometers. So that's all a good way to monitor that everything is the way you expect still. And you notice that when I pulled out the cuvette, the absorbance dropped down to nothing because there's nothing in there. There is no acetylsalicylic acid either at that analysis wavelength. Here are my data points. I'm going to expand the graph. That's looking linear, but how do I make sure I do a line? It looks like I have a, give me one moment to turn off the closed captions because it's blocking my buttons. Let's see. Okay, there we go. Okay, nope, that's still there. One more second. Okay, there's my linear fit. So I clicked that linear fit button. It's the graph with the line showing the dots, and that's a pretty good linear fit. I can not only visually tell that it is a decent fit because the points are either on or very near the straight line that is the best fit line. Also, if I look at the R, that tells me the correlation between the Y and the X values. They're highly correlated because it's very close to +1. +1 because it's an increasing slope. If I had -1, that would mean a decreasing slope. That would happen if I put these concentrations backwards. If I started high and went low, and I went from solution D through A, or actually, no, sorry, I misspoke. Because the relationship between absorbance and concentration is direct, you will see that when you are within that range between 0.2 and below the absorbance of 1, as long as you've got known concentrations, your absorbance should be showing a direct relationship indicated by a good linear fit. Your R is very close to 1. And if you wanted to, you could pull out the graph more towards the origin. If you notice this hand icon, if I click and hold the hand icon out in the graph area, I can move towards 0, 0, my origin X and Y, and I can see that although I'm not perfectly through 0, 0, I'm just barely on the Y-axis intersecting somewhere between 0.1 and 0.15. And if I want to know the exact value, I could look at the B value because that's the Y-intercept on the linear fit, 0.12. So this is linear. This is a good fit, and I can correct for any error using that B value in this fit. Okay, so now I've got some information here, almost enough to figure out how much aspirin is in a tablet. Let me go back to the directions. So far, we've got our Beer's Law plot for the 5 known solutions. So we've done this step. We've set our analysis wavelength. We've collected absorbance data for 5 known solutions. And we've plotted our absorbance concentration data. We've applied a linear fit to get the linear equation. And we're going to be able to do the analysis of the unknown concentration in aspirin. But wait, we've got to make some aspirin solutions and test their absorbance. So now I'm going to talk about how do we make a solution out of aspirin tablets. Okay, so I'm going to move the camera, go back to the camera, and give me a second here. Pardon the turning of the camera. I'm gonna have to actually spin it this way. One moment while I focus in on it and zoom in. Okay. Okay, so here's how we make the aspirin solution. You get the 325 milligram version of aspirin tablets from over the counter. Okay, so this is the regular strength aspirin, 325 milligram. Make sure that the expiration date, make sure the aspirin tablets are still good. But a fun thing to do is to, on purpose, get some expired ones, because you wouldn't expect expired aspirin to still be at 325 milligrams. You can actually see how much is left, how much acetylsalicylic acid is left in the aspirin tablets after they expire. Because these milligrams, the 325 milligrams of aspirin, is the same as saying 325 milligrams of acetylsalicylic acid. Okay, so these are regular strength aspirin tablets. You just need one. So you take the mass of one aspirin tablet, and obviously you don't use your hands, but after you got the mass of the aspirin tablet, you put in a mortar and pestle and grind it very smooth as you can get it. No chunks, make it very small particle size. The better job that you or your students do at this, the better your results will be when you analyze the aspirin. So you've recorded the mass of the aspirin tablet before you ground it, so that after you grind it up, you can get a very small mass of aspirin. In this case, you only get 0.0400 grams, or around there. So whatever mass you get of that powder, you take the powder, and you'll need a 100 milliliter volumetric flask, and you'll add your 0.400 grams from the powder into the flask. And again, you're going to get your isopropyl alcohol. So you get your measured mass, you pour it in, you rinse down with the same solvent, 91% isopropyl alcohol. And you swirl when you got about a third of the container filled with isopropyl alcohol. Swirl a lot, and you're trying to dissolve the any undissolved portion, anything that will dissolve from your aspirin sample. Now, there are some insoluble compounds in an aspirin tablet, like fillers and such. So after you've dissolved as much as you possibly can, if you've done a good job of really grinding down that powder, you won't visibly see any chunks, but it'll look cloudy because there are, like I said, insoluble compounds, and that's normal. So then again, you're going to fill up to your 100 milliliter line and complete your solution. And then you have this cloudy, unfiltered aspirin stock solution that you need to filter. So here's a filtration apparatus. I've got a Buchner funnel with, there's a, it's stuck in there right now, but there's a funnel in the Buchner, I'm sorry, a filter paper in the Buchner funnel. Okay, and you're gonna get some of your unfiltered solution to get that paper stuck in there. Make sure you got a good seal on your system. If you don't have a professional vacuum system, you can set one up with just some tubing, 2 Erlenmeyer flasks, your Buchner funnel, and a one-hole stopper with a couple of one-way valves. This is the syringe that you get either in PASCO's pressure sensor or with the drop counter. It's the same syringe, so that you can create a vacuum with it using this setup. Okay, so this is just the syringe, a couple of one-way valves, and tubing connecting Erlenmeyer flasks. Notice I've got where I'm going to filter, where I'm doing the filtering of the solution, I've got it nice and held in place on a ring stand. You definitely want to make sure that you secure this. You don't want that tipping over. Okay, so You get your unfiltered aspirin, you filter it through, and you collect your filtered aspirin solution down here. And this should contain the acetylsalicylic acid, but not any of the fillers. This is the stock solution that you're going to do your analysis with. Not this. This one should have all been filtered out. So now you take just a little bit of this. If you're doing a one student pair at a time, your students will only need 0.6 milliliters of this. So this is where you're going to get your pipette. You know, you just get your 1 milliliter pipette and carefully draw up the 0.6 milliliters in that, and in a test tube, add to 9.4 milliliters to get a total volume of 10 milliliters. So in this case, you barely need to make any solution for analysis, because you only need one of these to analyze in the spectrometer. And now I'm going to turn back to the spectrometer on the camera, so forgive me with the movement. It's a little bit dizzying. And I'm going to zoom back out. Okay, there we go. Let's scoot in a little bit. There. I'm going to bring back my solutions. So now we've got that step done. We're ready to test the absorbance of the commercial aspirin tablet solution. I wrote down some values that I collected earlier for the solution that I'm using today. The mass of the tablet that I used was this much, 0.3666 grams. And we know not all of that is acetylsalicylic acid, because we saw that cloudiness. You would have seen the cloudiness in the solution that you made. And then we're going to record this number 2. How much powder did we actually add to the solution? On my balance, I got 0.0411 grams. Okay. So the next thing we do is we're going to go back into spectrometry. Here we go. And notice I haven't hit stop yet, but if I hit stop, it wouldn't be a problem. I can just hit record again. So now I've got my Beer's Law plot. I'm going to rescale, and I'm going to test the absorbance of that aspirin solution, the filtered aspirin solution that I made. Okay, so that goes into the spectrometer. I have to click the box down here on the bottom where it says determine unknown concentration. So I click the box and I see this red number. That's the absorbance of the aspirin solution I made with the steps that I just explained. I'm going to keep that value. I know the absorbance of 0.555. Oh, look at that. I happen to have that value exactly, or almost exactly on my y-axis. Here it is, 0.55. There's a few ways that I can try and estimate the concentration now. Because I know absorbance is 0.555, if I move over and I can see exactly where do I hit that line of best fit, and I go straight down to the x-axis, I can see my concentrations between 0.12 and 0.13. Now I can do a little bit better than that. Maybe I can use a ratio or proportion. I can say, well, if 0.222 moles per liter has an absorbance of 0.874, then some concentration that would be equal to whatever concentration of this aspirin over 0.555. So I can set up a proportion that way, but why would I do that when I've got this great data here? I got a line equation where I can solve for the unknown concentration. I have everything I need to use a linear equation. So I'm going to go back to this slide and explain how to do that. So like I said before, we can solve for, if you wanted to, you can use a proportion, any of the absorbance concentration pairs that are known that were recorded a minute ago, or we can figure out X and plug in that absorbance that we read for the aspirin tablet. It was 0.555, and just calculate X. But the better way to do it is to use the line equation. Okay, let's look at the values for that line equation in spectrometry. Here they are. Y equals mx plus b. So we know Y. What's on our y-axis? That's absorbance. We know Y, right? And Y, our absorbance was 0.555. So I'm going to start plugging in Y to this equation. Absorbance has no units. M, well, that is here in, sorry about the on-screen chaos. So we got M of 0.34, or my slope, 0.340. And because it's absorbance per concentration, it's millimolars to the -1 is the unit. X is not known. What is X? Again, that X is on the x-axis. That's concentration. We don't know the concentration. That's what we're trying to figure out. Plus B. And B, according to spectrometry, is 0.122. So if I solve, I can just calculate this very quickly. Let me bring up a calculator on screen because I'd rather not do this in my head. So it is 0.555 minus 0.122. I've got 0.433. Oops, I'm sorry. Should be letting you see my calculation here. There we go. Okay, I've got 0.433 equaling 0.340 millimolars to the negative first power. And when I divide that out, times x rather, when I divide that out, x is going to equal, let's see, divide that by 0.340, I get 1.27. Okay. Alrighty. Let me go back to the math here. So far, what is x? X is concentration, that's millimolar. I figured out the concentration of acetylsalicylic acid in the solution, but that doesn't tell me, I know the concentration, but that doesn't tell me, is it actually 325 milligrams? I need to do some math to get some conversions to get over to that grams value. So now let me get some more calculations done. Let me write down the number I got a minute ago, 1.27. Oh, we can use, oops, sorry, 0.127. I think I did something. Let me check my work here. 0.433. Oh, it was 3.4. Yes, I had missed a decimal place. There we go. And then that would be 0.127. I thought that was a bit high. So pardon me, 0.127 millimolars was the actual concentration. My mistake. And this is good. You know, students might make a mistake. And hey, there's a tool built into spectrometry that helps you figure out if you made a mistake. Let's say I didn't recognize that I did something wrong and I just thought, oh, my concentration is 1.27 because I accidentally moved the decimal place in the wrong spot. If I come here to this graph where it says determine unknown concentration and I plug in that concentration value that I just solved, 1.27, and then I have to hit stop now. So it has to have stopped recording. So I put in the concentration. I have a concentration absorbance, but I don't see it on the graph. Well, where is my concentration? Let me scale. Oh, look at what happened to my graph. I have this red X far off to the right. My software is telling me, whoa, you really messed up that concentration. You did something wrong. You better go back and check your work. So even if I hadn't caught my error, the software helps me realize I made a mistake. So let me quick go back to the slide here. And when you see these symbols, like I just got this huge error, I've made a big mistake. It tells you, oh, you're way off. You better go back and check your work. My goal is to see the little bright green circle, because that means I've got less than 5% error, and the brighter the green, the closer to 0. The darker the green, the closer to 5%. If I'm over 5%, I'm close to 5%, but a little higher, then I'm yellow. The closer I get to 10%, the more brown it looks. So now let's put in the corrected concentration, because I moved my decimal place on accident. Oh, look at that. It's that bright green dot I wanted. It should go on that linear equation based on the math you just did. It should fit on that line or very close to it or directly on it. Okay, so there's that built-in feature to check your work for your concentration. Spectrometry has helped us not only solve our problems, it's also given us the information we need to finish our calculations here. Here we go. Here is this analysis of all the math that we have to do from that concentration that we just got, that 0.127. We've got to convert that concentration back and figure out what is the concentration in that cloudy solution. Because if we get the concentration of that cloudy solution before we filtered it, we can figure out what's the mass of acetylsalicylic acid in that stock solution. And if we know that, we can figure out, well, what percentage of that powder is actually acetylsalicylic acid. And if we know the percentage of acetylsalicylic acid in a small sample, we can then apply that percentage to the entire tablet to tell us how many grams of acetylsalicylic acid are in the whole tablet. And I'm going to walk through each of these calculations in a second. Then finally, we can compare and see, are we within 10%, plus or minus 10% of 325 milligrams, because that is the standard set by the US pharmaceutical and national formulary standards. Here we go. First, we need to figure out what was the concentration in the back here on this first unfiltered aspirin solution. So let's do that math. We've got to figure out concentration 1, M1. So concentration 1. Well, we know M2 at V2. M2, we got that from using the spectrometer. That concentration of 0.127 millimolars was the concentration of the second solution that we diluted. And we made 10 milliliters of it. Divide by V1, we added 0.6 milliliters. And if we cancel and do the math, gotta bring up the calculator. Again, I'd rather not do calculation in my head. Where'd it go? Give me a second while I find my calculator. I'll have to close it and reopen it to get it to come back up. There it is. Okay, so my calculator, I've got 0.127 times 10. Divide that by 0.6. I get 2.12 millimolar. Okay, that looks right. So I'm going to write that down. Got to keep track of my numbers, 2.12 millimolar. Because now I have to convert that 2.12 millimolar. I've got to get that into grams, but I've got to worry about units. Okay, so first I'm going to change millimolars back to moles. So there are 1,000 millimoles in 1 mole. And I didn't exactly have a liter, I only had 100 milliliters of it. So I had 0.1 liter of that powdered solution. So I got to convert that from milliliters to liters. And then finally I have to multiply by the formula mass, 180.16 grams per mole of acetylsalicylic acid. And now I can get my way from the concentration using some conversions to get to the mass of acetylsalicylic acid. Here we go in the calculator. 2.12 times 0.1 times 180.16, and I'm going to divide that by 1,000. Okay, I've got a mass of 0.0382 grams. That's how many grams were in this solution of acetylsalicylic acid from the tablet. Okay, I'm going to write that down. 0.0382 on the side here so I don't forget it. Next, I'm going to figure out what percent of the powder was actually acetylsalicylic acid. All I have to do to solve that is get the grams in solution that we just calculated, which was 0.0382 grams. Divide by the powder added. I remember earlier I said I wrote down those values I got before. I took the masses before we came online here. So 0.0411 grams is what I got out of my balance. And if I calculate that, let me just divide this by 0.0411 and multiplying that by 100, we get 92.9%. So that's just how much of the powder was acetylsalicylic acid. I'm going to write that down real quick. Next, so that 92.9%, I'm just going to convert it back into a decimal. 0.9, I already forgot what the number was. I have to go back and check. 929. So that's the percent ASA in the powder is equal to the grams in the ASA in the tablet, which we got, which we don't know. So we're trying to solve for the grams of ASA in the tablet. Divide by the whole tablet mass, which remember before I said I already got the mass of the tablet. My tablet was 0.3666 grams. Okay, and when we solve for grams, so let me go on my calculator. We're going to take the 0.929 and multiply by the mass of the tablet. And that gives us 0.341 grams of acetylsalicylic acid in the tablet. Okay. Or I can convert this to milligrams and say, oh, there's 341 milligrams of acetylsalicylic acid in that tablet. Oh my goodness, that's more than what it says on the bottle. But is that a problem? Is that a problem? Well, let's see what the USP standard says. Remember, it says plus or minus 10% of 325 milligrams is acceptable. So finally, the last step here, the percent difference, we get the grams of ASA in the tablet, which again, I have to go back and look at. It was 341 milligrams, or 0.341 grams, over. The bottle says 325 milligrams or 0.325 grams times 100 to see what's the percent difference between one tablet and what it says. And let's divide that by 0.325, multiply it by 100. It's 105%, which is acceptable because the standard says plus or minus 10%. We got 5% above, which makes sense because this is pretty fresh aspirin. It expires May of 2024. So that's a few years from now. So that is how we get the percentage of aspirin in an aspirin tablet using common substances. Now, a couple quick things I wanted to show you in spectrometry. You might be wondering, hey, I want to do more analysis in Excel. You can do that. If you go to the share icon, you can do export data, and that will give you your data in a CSV file. You can use that in another spreadsheet program. Or if you're not quite sure, you remember how to do something, you can always go to the gear and click help, and that will open the online help on the PASCO website. Let me bring that over so you can see. It brings up this help screen on the web, and you can just search for whatever it is you're trying to get help with. Okay. Next, let me move back on to this presentation. Here's where I got the experiment from. It's from the PASCO experiment library. Here's how you get there. Now, if you go to pasco.com and you go to resources, there's experiment library there on the left. You can search aspirin and that lab will come up, analysis of aspirin tablets. So if you're logged into your teacher account, which is free if you don't have one, it will give you the answer key as well. And also a video. Some of the experiments here have videos, some don't. Some have sample data, some don't. Just take your time, check this out. If you want to just see what other UV-Vis labs there are, you can just type in UV-Vis in the part, and or you can type in the product number SE-3607 and choose it, and then hit the filter button. And I didn't put anything in the search phrase, so everything's going to come up for that instrument and more. Okay. All right. So now I'm going to hand this over to Roger for a little bit more on what else you can do with the UV-Vis spectrometer.
Thanks so much, Barbara. I'm excited that you guys have a chance to see one of our labs in action here, but that the idea of a UV spectrometer is important because it fits in lots of places you might have in your work sort of scenario. If you're a college instructor, it's great for first year chemistry, general chemistry, all the way to physical chemistry. It can measure sort of absorptions or emissions, determine physical constants, be able to determine concentrations like we saw here, and is a great tool for that. It can be used as second year kinds of sciences in organic chemistry or biology chemistry, or absorption of biological molecules you might be interested in, and be able to use in those kinds of scenarios. It's also a great tool for analytical work or instrumental classes, people that are taking maybe forensic sciences, and it's an awesome tool to be able to use. So it really does have a broad use across the spectra of classes. We also have a nice background material in some of our guides that your students can access, that you can see more about spectroscopy at pasco.com/product/guides. We'll also put a link, to look for spectroscopy, but we have other kinds of topics as well. We'll just put a new one up on titrations as well. That's in terms of chemistry, and you'll see other things for the other fields of sciences we cover. So that's a nice resource that students a lot of times will use, to feel free to grab from if they're needing some even imagery for lab write-ups. This spectrometer, the UV-Vis, is part of our family of spectrometers, and you can see that we have things that are even as simple as the colorimeter that can be used to look for things like just water quality. We have, they just look across the red spectrum. It's not as fine detailed as you saw in the spectrometer here, where you can see down to the nanometer these peaks, but they can see how much red is absorbed or blue is absorbed, especially if you're using water quality ampules to determine nitrates or phosphates or something. The visible spectrometer is very similar to what you saw in terms of the interface, but obviously it's got a narrower range of spectra that it can use in the visible, 400 to, well, 8, 9, well, I think it's 1,000, but it's in the visible range and a little bit in the infrared. It does not go down into the UV. The polarimeter is great for chiral molecules or organic molecules, and it will determine the concentration of molecules that have a handedness. A lot of biological molecules or sugar or food molecules can have a handedness to them, and you can use them to determine the concentration of those solutions. And of course, then the UV-Vis, of which we've highlighted. Just a quickie, it's very similar in terms of the process that the UV and why it's good for organic molecules, particularly molecules that are white, that don't show, what their substance is. If you look at copper, it's always blue, for instance, and those metals that you would use in flame tests, for instance, that's from electron transitions around an atom, as you see in the bottom of this picture. That atom, when it absorbs energy, either being excited electronically or from the flame, when those electrons come back to their ground level, are falling back to like an S2, well, a second level orbital, as a Bohr electron orbital goes, and they're usually in the visible. That's the visible light you see when those electrons are falling back down into that level, and it determines, those colors are shown determine which the element is in the metal, or if it's a gas and it's been excited electronically, especially if it's a single element, that you can really see those electrons falling around atomic level. The UV is important, though, for molecular transitions. Just like an electron can fall from further from the nucleus to closer to the nucleus, they can fall in different patterns. The classic example is it really helps you to understand molecules with double bonds. You can see in this example and that you can excite an electron that's in a bonding sort of an orbital, even just with one double bond, and that will go to an antibonding orbital, or that'll make a jump to a different shaped path. But that energy is a lot. It's down there below 200 nanometers, and usually you can't see those. So the more double bonds you have, the closer that jump is to an excited or a different vibration path across that whole molecule. So what I'm saying is that either having several double bonds, conjugated bonds, or a benzene-like structure where you have 6 carbons in a hexagon with double bonds that make it aromatic, those are going to be the kinds of compounds that you'll be able to tell the concentration of for chemical experiments. You say, well, what importance are they? Well, here's just some of the molecules you might be able to study, not just aspirin, but any of the pain relievers, ibuprofen, naproxen, sodium. The drugs that are available are all usually have aromatic rings, double bonds that can be studied, and you can see their concentration. So many times these UV can be used to determine how much concentration you have, or if it disappears, you make a reaction so that it goes away. You can just study the rate at which those chemical reactions either make it destroyed, or that you create it. If you're making a reaction and you're creating that, you can follow those. You can follow food and nutrients like vitamins, vitamin A, B, C, and study food chemistry with the ultraviolet sort of spectra. And flavorings are fantastic, and so all of these are great for use in like I said, organic labs or as food labs, or in quite a broad range. That's a great skill to have, and it's a useful tool, very much important. The 2 concepts that I'll just relate to you, that is, if they have a benzene ring or a 6-membered ring that has double bonds at every other place, the very left you'll see a sort of black looking, I think actually it's dark blue looking spectra, and that's right around 250 or so. that absorption occurs. That's typical for that kind of a molecule in what you want to study. Now, is that the only thing that can absorb those? No. But what I wanted just to say is that as you get more and more rings, you'll see that that spectra slides to the right. And that's what you can use, again, to determine how much of any one of those substances you might have that you're interested in. Double bonds in a straight chained hydrocarbon is also absorbent down here in the ultraviolet, and that's what you'll want to use this tool to determine. But it does need to have several that are every other bond. They're able to be conjugated or dispersed. That double bond can move, the electron density can move across that molecule when they're that close. You'll see as you get more and more in the image there that you will see that the spectra, if you have 6 or 7 double bonds that are every other one, you can see the spectra absorbs and makes the absorptions at higher and higher levels. And that can help students to understand what the molecule is made of. I'll finish out by saying, if you get the idea that the bigger and more double bonds you have, you slide to the right. The two things that I wanted to point out here, you don't even need to necessarily have, the benzene ring in that first example. Prednisone is a great steroid. It's a biological molecule, and it has every other atom has a double bond. It doesn't even, the double bond to oxygen plays a part in a delocalized place for electrons. And notice it's got 3 double bonds. It's got an absorption down at the same place that the 3 double bonds of benzene is. If you put an electron withdrawing groups, the bottom right picture, you'll see that pulls the absorption more to the right. It takes less energy to jump between the last highest occupied orbital to unoccupied. So if you put oxygens or nitrogens onto those compounds, you're going to see the spectra slide to the right. If you put carbon change, you see the spectra slide to the left. So as a concept, we just want to make sure that using this tool can really be used across chemistry. And those are just some simple concepts that can be applied. Once you know those heights, you can determine concentrations and determine things that you want to do in your labs. So we really thank you for your time. We're going to go ahead and turn it over to Barbara.